AmishaKapoor, and this is my Lab 4 video report for Physics 2212. So, the general purpose of this lab is to allow for students to experiment with Faraday's law and how nature offsets the change of flux via dropping a strong magnet in a conductive tube. I, in specific, learned how strongly the size of the radius of the ring itself can impact this effect, with it taking significantly longer for the magnet to fall through the tube with a smaller inner radius. I also found that in simulation, that it takes around 1.78 seconds for the magnet to fall, versus in real life it takes about 1.852 seconds as part of my results. As for general principles used, we use the law F equals ma. We also use the principle of EMF equals to change in potential voltage equal to IR. We use the Biot-Savart law as it's the basis for solving for magnetic fields, and that's integral whenever you're looking for the change in rate of your flux, as the change in rate of your flux is equal to your EMF, and that divided by R will give you like your current. And using that, you can find things like your force, and see how the two forces, the force of gravity and the magnetic force, interact with each other. And then for the simulation itself, we use the velocity and position update formula. And actually, in regards to what I said about force, we also know that F net is equal to F1 plus F2, which is integral because in order for us to reach terminal velocity and actually have the flat part in our graph that you'll see later on, we have to have F net equal to 0, which is only possible if you have your negative mg plus a positive magnetic force. So during the actual experiment itself, I essentially took a bunch of trials, 5 trials in specific, of dropping the magnet down, north side down, into the tube. The first time got 2 seconds, the second 1.98, going all the way to 1.84 seconds. As for the tube itself, the tube is made of aluminum foil. What we know is, some of our constants, like 1 times 10 to the negative 7. We know our resistivity of aluminum, because this is aluminum tube, just 2.65 times 10 to the negative 8. We have our gravity constant, which is 9.81. And then we have our known length of the tube, which was 0.30 meters, as it was 30 centimeters. The inner radius of the cardboard tube on the inside is 0.0230 meters, and the foil's width is 0.01 meters. And so the average time we found from our experiment was 1.852 seconds. And also, in general, important premise is the fact that the source within this situation is the magnet, and like our observation point in our system is going to be based off of the aluminum foil, which we are modeling in rings. As for the checkpoint from the experiment, we found that ferrous tubes can act as a magnet, as they can the magnet that we're dropping the tube can induce a magnetic field from a ferrous tube, so that will also interfere with the magnet compared to it just being the flux, the change of flux interfering. Additionally, by opposing the changing of flux due to gravity, essentially, this is based off of Lenz's law. So if we were to drop the magnet in a completely open area, it would fall faster than us dropping it in the tube because there is no change in flux, which is particularly impacting it and making it fall slower due to opposing the movement. And then some of our other values is the mass of the magnet, which is 0.023 in kilograms, and mu mag, which I got from our second lab. As for the code itself, the top left code is my lab 2 code, which is just for a dipole, as the magnet, being north and south, can be modeled as a dipole. So that is my code there. And then the next bit of my code is in relation to actually calculating the change in our flux over time. And so for that, I got for my numerator 3 over 2 times our previous constant, which was mu naught over 4 pi. And we actually ended up canceling some of that because we have the 4 pi later on. And we multiply it by the magnitude of our mu and our distance, as well as our speed, which an important thing to note is distance is the distance between our observation point, which is like in the tube, versus where the magnet currently is. And then we have our denominator, which is the radius of the ring, plus our r vector, or our distance, squared, and all of that raised to 5 over 2. And our df dt is just us putting together the fraction and us returning it. And so, on the other hand, we are putting everything together. So I define our force of gravity as -1 mass times gravity. And then we go down to the bottom, and essentially, we aren't making like many major changes here. I think the only thing that I slightly edited was the magnitude of force on the ring. And then, other than that, it was just using our F net is equal to F gravity plus F magnetic, and then updating our velocity and position. And then you see on the bottom left what our graph ended up being. We got around the time of 1.788 seconds, which is, like previously mentioned, a little bit lower than what we got in real life, which was around 1.852. And so there are a few potential reasons for this, but we will get to that in a second. So as for the what if questions, one of them is what happens if the resistivity of the conductor was reduced to be as close as possible to 0? And my response to this is that we would experience a very, very strong repulsion upward. Why is this? Well, in the process of calculating for your I, or your current, you have to take your change in flux and you have to divide it by R. And so if you were to reduce R as close as possible to 0, so it's not undefined, but at the same time it's incredibly, incredibly small, then you would end up with a very, very large current. Considering that your current is utilizing the formula to find your force, that would create a very, very strong force upwards, essentially causing a repulsion. And then if we were to have holes or slots cut into the tube, there'd be a decrease in the flux at those holes or slots. And that's kind of because, in a sense, we're losing the area that we're kind of falling through. And there's it's an incomplete, I guess, loop in a sense. So because of that, the current within those areas are dropping to 0, or effectively dropping to 0. It really depends on how the holes are cut. And so so I would say in total, because of this, and because we're having so many places where we're having this drop, there's less points of repulsion. And with us having less points of a strong repulsion, we're going to end up falling through the aluminum tube faster. And then as for sources of error, in totality, I think there might have been a few points. One of them is slight errors in time collection, like I might have been a few milliseconds off here and there, but this really only impacts our comparison between the simulation and our real life, I guess, experiment and seeing how closely they compare. And then I would also say I have likely had slightly inaccurate foil dimensions, and this is because I do not have the most efficient methods of calculating my foil, and the foil I do have isn't like completely rung tight, and so there's kind of space in between some of the foil, and because there's space in between some of the foil, that's kind of increasing the radius, and that can cause for some small inaccuracies in the calculation. Lastly, one other, which I believe was an important impact on the time differential, was the fact that in the first situation, which is the experiment, you could have air resistance, which further is really slowing down the magnet from falling through the tube, kind of adding its force upwards. But in the other case, which is a simulation, which is purely ideal, so all we have is our magnetic force, and all we have is our force of gravity. Because we're not accounting for air resistance, we're going to fall through faster than if we had. Thank you.